Have you ever stopped to think about the clothes you're wearing? I mean, really think about them. Today, we're going to peel back the layers on your favorite shirt or jeans and reveal the absolutely incredible science and engineering that's hidden inside every single thread. Let's dive in.
So, go ahead, take a look at what you're wearing right now, and ask yourself a simple question. What is this thing really made of? And look, if you said cotton or polyester, you're not wrong, but you're only just scratching the surface. The real answer is way more fascinating. It's all about a constant battle between order and chaos, right down at the molecular level.
You see, everything you wear is the result of this incredible journey. It starts with molecules you can't even see, which then build up into these complex coils, which then get bundled into filaments and eventually become the fiber that makes up your clothes. It's a total masterpiece of microscopic engineering.
So to really understand that engineering, we've got to start with a blueprint. In this first part, we're going to look at that fundamental conflict that's right at the heart of every single fiber, that battle between order and chaos.
Okay, so every fiber, doesn't matter if it's natural like cotton or synthetic like polyester, it's built from something called a polymer. Just picture a super long chain made of all these repeating links. And for that chain to make a good, strong fiber, it needs to be really long and, pretty straight. And these long chains can exist in two main ways, which this slide explains perfectly with my favorite analogy, spaghetti. On one side, you've got crystalline regions. This is where the chains are packed together, super orderly, perfectly parallel, kind of like a neat bundle of uncooked spaghetti. But then you have the amorphous regions. This is total chaos, where the chains are all tangled up with no order at all, just like a messy bowl of cooked spaghetti.
Now, why does this matter? Well, this difference in structure has a huge impact on how a fabric feels and performs. That orderly, crystalline structure, it creates super strong attraction between the chains. That means you get high density and it's really tough against chemicals. The chaotic amorphous side, the forces are weaker, the density is lower, and it's way more vulnerable. This is literally where the personality of your fabric is born.
But here's the kicker. Almost no fiber is 100% one or the other. It's a mix. They follow what scientists call the fringed micelle model. You have these little islands of order, the crystalline bits, that are floating in a sea of chaos, the amorphous regions. A single polymer chain can weave in and out of both zones. It's this combination that gives fibers their amazing blend of strength and flexibility.
And the cool part is, we can actually see this stuff. When scientists fire X-rays at a fiber, the pattern it creates tells a story. Look at this graph. You see those sharp, spiky peaks? That's the signature of the ordered crystalline parts. And those broad, rolling hills? That's the chaos of the amorphous parts. It's like a fingerprint of the fiber's inner world.
Okay, so now that we get the blueprint, let's see how it's actually used to engineer the fabric. In this next part, we're going to go from that molecular blueprint to the actual clothes you wear.
What's just so amazing to me is that the feel, the strength, the performance of your clothes, it is not an accident. Manufacturers deliberately engineered this ratio of crystalline to amorphous regions to get the exact properties they want. It's the difference between a tough-as-nails pair of jeans and a super soft t-shirt. And as a general rule, the more of those ordered, crystalline regions you pack in there, the more robust the fiber gets. We're talking higher strength, more durability, better resistance to chemicals, and it even soaks up less water. It's basically the formula for a fabric that lasts.
So how did they do it? Well, one of the key tricks is a process called orientation. They start with the raw polymer, where all the chains are just a random mess, right? Then they physically stretch it and pull it. This forces all those chains to line up parallel to each other. Think of it like a tug-of-war team. When everyone's pulling in a random direction, you go nowhere. But when everyone pulls together, you get this massive increase in strength. That's exactly what's happening here.
But creating a strong fiber is really only half the battle. Now we're going to explore the invisible forces that are literally holding your clothes together as we speak.
First up, let's talk about friction. We usually think of friction as a bad thing, something that slows us down. But in textiles, it is the unsung hero. When tiny fibers are twisted together to make yarn, it's the friction between them that stops the whole thing from just puffing apart into a fluffy mess. It's the glue.
But as you can see here, friction is a real double-edged sword. On the one hand, you absolutely need it. It helps hold the yarn together, it maintains tension, it's crucial.
On the other hand, it causes wear and tear on machines, it can actually break the yarn if it's too high, and it even generates static electricity that makes your clothes attract dust and dirt. It's a constant balancing act for the engineers.
All right, next up is a force you have definitely 100% experienced. It's called creep. You know how the knees in your favorite super comfy sweatpants get all baggy and stretched out over time? Yep, that's creep. It's just the slow, gradual stretch a fabric goes through when it's under a constant load, like, your knees bending all day. This graph basically shows us the entire life story of a fiber under that kind of stress. So as soon as you put a load on it, you get this quick initial stretch. That's primary creep. Then it settles into this long, slow, steady stretching phase called secondary creep. Finally, the structure starts to give up, the stretching gets faster, and eventually—
And the most important thing to get here is the difference between a good stretch and a permanent sag. That initial primary creep, it's mostly elastic. The molecular chains are just being pulled a little bit, but they can bounce back. But that long-term secondary creep, that's permanent deformation. The actual chains can start to break and slip past each other. And that is the difference between a fabric that snaps back into shape and one that just sags forever.
So let's bring this all together. Let's zoom back out from the microscopic world and see how all of this science shapes the clothes you choose to wear every single day. Let's reimagine your wardrobe.
So we've gone on this whole journey, right? From the invisible dance of polymer chains bouncing between order and chaos, through the forces of friction and creep that decide how fabrics behave, all the way to the real-world things you feel right now. The strength, the comfort, the very feel of the shirt on your back.
At the end of the day, the one thing I really want you to take away from all this is that every single fabric you own tells a story. And it's a story of science, of intentional design, of molecular architecture, and some pretty cool applied physics.
And that just leaves us with one final, fascinating question. We've pretty much mastered the engineering of materials like cotton and polyester, but right now we're entering this new age of smart materials, of bioengineered molecules. So what's the next chapter of that story going to be? What will the clothes of the future even feel like?